Welcome back to the computer lessons.
Light consists of photons carrying electromagnetic energy through space at the maximum physical speed allowed by the universe. When these particles strike a digital sensor, they trigger the photoelectric effect within the crystalline silicon structure. This process converts individual photons into free electrons held in microscopic capacitors for data processing. The CMOS sensor serves as the primary electronic eye for modern civilization, replacing traditional film with silicon. It features a grid of light-sensitive pixels integrated with specialized readout circuitry and amplification. CMOS technology revolutionized imaging by allowing high-speed data processing directly on the chip for mobile devices. Each pixel contains a photodiode acting as a microscopic light bucket during the specific exposure interval. As light enters, it passes through filters and lenses before reaching the depletion region of the silicon. The number of electrons collected is directly proportional to the light intensity detected. Silicon atoms release electrons when hit by photons, overcoming the specific energy band gap threshold of the material. These electrons are trapped within a potential well, defining the pixel's fundamental full well capacity. Once capacity is reached, the pixel saturates, resulting in clipped highlights and lost detail. To read data, accumulated charge transfers to a floating diffusion node located within the individual pixel. This charge is converted into a voltage signal by an internal source-follower amplifier circuit. CMOS sensors perform this conversion at the pixel level to ensure maximum processing speed. Historical CCD sensors moved charges across the entire chip to a single corner for conversion and readout. This bucket brigade method was accurate but slow and consumed significant amounts of electrical power during operation. CMOS sensors replace them by integrating amplifiers and digital converters onto the same piece of silicon. Integration of analog to digital converters at the column level allows for massive parallel data processing. Thousands of columns can be read simultaneously, enabling high frame rate video for modern smartphones and cameras. This architecture reduces the time required to empty the sensor after each physical exposure cycle. Silicon sensors are naturally monochromatic, meaning they can only measure the quantity of light, not color. Without filters, every digital camera would only produce black and white images based on electron counts. To capture our colorful world, engineers must apply a physical mosaic of transparent dyes. The Bayer filter array is the standard solution for capturing color information in a digital sensor. It consists of tiny color filters placed directly over each individual pixel in a specific pattern. This mosaic consists of 50% green, 25% red, and 25% blue filters. Green is prioritized in the Bayer pattern because the human eye is most sensitive to green light. This sensitivity mimics our biological perception of luminance and detail in the natural environment. By sampling green more frequently, the sensor can produce sharper images with more accurate perceived brightness. Converting this raw mosaic data into a full-color image requires a complex process called demosaicing. Mathematical algorithms analyze neighboring pixels to interpolate the missing color information for every single site. This reconstruction logic allows each pixel to eventually have a calculated red, green, and blue value. Signal-to-noise ratio, or SNR, is the most critical metric for determining the overall quality of an image. In low light, the number of photons hitting the sensor is low compared to electrical noise. This interference creates the grain or chroma noise that degrades clarity in dark scenes. Increasing the ISO setting on a camera does not make the sensor more sensitive to light. Instead, it increases the electronic gain applied to the voltage signal before it reaches the ADC. While this makes the image brighter, it also amplifies the background noise and reduces range. Dark current is a form of thermal noise caused by electrons jumping within the silicon without light. Heat causes atoms to vibrate, occasionally releasing an electron that the sensor misinterprets as a photon. Long exposures and high temperatures exacerbate this problem, leading to hot pixels and artifacts. Dynamic range measures the sensor's ability to capture detail in both deep shadows and bright highlights simultaneously. It is determined by the ratio between the full well capacity and the noise floor. Professional sensors utilize 14-bit or 16-bit ADCs to preserve these subtle tonal gradations effectively. Pixel pitch refers to the physical size of each individual pixel, measured in microns across the chip. Larger pixels have a higher surface area and can collect more photons per unit of time. This is why large sensors generally perform better in challenging low-light conditions than smaller ones. Smartphone manufacturers often use high megapixel counts on tiny sensors to appeal to consumers through marketing. However, packing 100 megapixels onto a small chip results in microscopic pixel sizes with poor SNR. Computational photography must then work aggressively to clean up the resulting noise and artifacts digitally. Quantum efficiency represents the percentage of photons hitting the sensor that successfully produce a measurable electron. Modern engineering has pushed this efficiency toward 90% using specialized microlenses. These tiny lenses sit atop each pixel to focus incoming light directly into the sensitive photodiode. Back-illuminated sensors, or BSI, represent a significant leap in sensor design by flipping the internal structure. In traditional sensors, the metal wiring sits above the light-sensitive layer, blocking some incoming photons. BSI sensors place the wiring underneath, allowing light to hit the silicon die directly without obstruction. Dual-native ISO technology uses two separate electrical paths for signal amplification within each pixel circuit. One path is optimized for low ISO cleanliness, while the other is designed for high-gain performance. This allows cameras to capture cleaner images at high sensitivity by switching to a cleaner circuit. The method of reading data from the sensor introduces specific physical constraints known as the shutter type. Most CMOS sensors use a rolling shutter, which reads the pixel rows sequentially from top to bottom. This creates a small time delay between the top and bottom of a single frame. This delay causes the jello effect, where fast-moving objects appear distorted or slanted in the image. To solve this, high-end sensors utilize a global shutter that reads every pixel simultaneously. Global shutters require more complex circuitry, but eliminate all motion distortion for high-speed scientific applications. Video recording requires the sensor to process data much faster than for still photography tasks. Some sensors use line skipping to reduce the workload, which can cause aliasing and more patterns. Higher quality cameras use oversampling, reading the full sensor resolution and then scaling it down digitally. The Image Signal Processor, or ISP, is a dedicated chip that handles the massive flow of data. It performs noise reduction, sharpening, and color correction in real time as the data leaves the sensor. The ISP is responsible for the final look of the image before compression occurs. Computational photography utilizes the speed of modern ISPs to merge multiple exposures into a single file. This enables high dynamic range, or HDR, imaging on sensors that would otherwise clip highlights. By capturing and combining images in milliseconds, we overcome the physical limits of small silicon chips. Stacked sensor technology places the processing circuitry and memory directly behind the light-sensitive pixel layer. By bonding multiple layers together, engineers can include a buffer of DRAM on the sensor. This enables incredible readout speeds, allowing for super slow-motion video and blackout-free electronic viewfinders. Our detailed analysis of the silicon eyes that capture our world concludes here in mobile technology. In our next technical video, we will explore wireless charging physics to see how energy moves. We are transitioning from capturing electromagnetic light to utilizing electromagnetic induction for portable power.
The CMOS image sensor is a masterpiece of electrical engineering that bridges the gap between physics and art. Mastering these technical concepts allows you to understand how machines interpret our colorful visual reality. Do you prefer high megapixel resolution or larger physical sensors for your digital photography? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.